So yeah, can you hear me clearly now? Can you confirm? Can somebody confirm that you can hear me clearly? Okay. Uh, yeah. So let's start. So welcome to week 6 of Introduction to Polymer Physics course. We are discussing phase separation of molecules in detail. We have already discussed some example problem. You have already tried out the assignment, I guess. So I will quickly go over the previous week assignment and discuss the solution in brief. I will try to finish this quickly and continue this week content. So problem number 1 was like, so during the phase transition, so discussing about phase transition of like ice to water, water to gas, these are solid to liquid, liquid to gas. With the increment of temperature, we are discussing the phase transition of uh, material. Uh, Day-to-day life example is phase transition of water, but that can happen to any other material with the increment of temperature. With the increment, if you heat up the material, there will be state of change, change of state, and there will be phase transition. So during this phase transition, what happens? There are multiple options that what happens to order. So two specific question: what happened to order and what happened to entropy. So clearly, as we have discussed multiple times, that suppose let us take the example of ice here. So ice is a regular arrangement of water molecule. If you heat this sufficiently and go beyond the melting point, it will be liquid and you will find this as water. If you heat more beyond the boiling point, it will be gaseous molecule. So in the gaseous state, water vapor molecule, there is no particular order between the molecule. So you will find the molecules at a random position. There will be no particular preferred position with respect to one molecule to another molecule. There will be no particular preferred position. But in the contrary, if you look at this I state, there will be regular arrangement of molecules. You will find the molecules at regular intervals. There will be a order, and it will be a perfect crystal if you go sufficiently low temperature. Not necessarily if you will find that as ice is a perfect crystal, but it will be more like a crystalline structure, and there will be a regular order. You can find out that order is there, but in water there will be only short range order. You won't find a very long range order. There will be no correlation between the position of very uh, far away molecules, but in the short range, in the neighborhood of one molecule, there will be a order, there will be interaction. As we have talked about that interaction many times, that van der Waals interaction and will be there, but it will act only at the short range. So during the phase transition from gas to liquid, from gas to liquid, so we are going in this direction, opposite direction, gas to liquid. So order sub is increasing, because in gaseous state there is no particular order, but in liquid there is some order is there, so order increases. But order increases means there will be less number of preferred uh, configuration possible, because molecules are getting its fixed position, so there won't be not much entropy in the system, so entropy will decrease. These are the consequence of phase transition. Entropy will decrease. Similar thing happens if you go from liquid to solid. Order will increase more and entropy will decrease further. Okay. So yeah. So gas to liquid, order increases, entropy decreases. Let us move to next question. Question number 2. For an ideal chain, G of R is what? How it is dependent on R, as a function of R, how it is dependent on R. So you already know this formula, that G of R goes like R to the power 1 by nu minus d, where nu is the same exponent we have discussed in the module of random walk and other polymers, Flory theory, or those, that r square influence distance or radius of gyration, whatever you like, mean square into distance, m is the number of segments to the power nu. So this new this new exponent is same as this new G of R dependence, and d is the dimension. So for an ideal chain, R square average, RE square to be precise, this goes like so. Yeah, so this is this if you define this as Rg, if I define like this, Rg is m to the power nu. So for an ideal chain, Rg is m to the power half, so nu is half, and we are talking about 3 dimensions, so d is 3. So G of R goes like R to the power 2 minus 3, that is 1 by R. So you have to remember this formula only, and using this formula you can easily get the dependence. So similarly for other kind of chain, so this ideal chain behavior is for theta solution. So there will be two more kind of solution, that will be bad or poor. Theta solvent is the ideal chain, bad or poor solvent, their nu will be something like 0.33, or there will be good solvent where theta is like 0.6. Okay. Okay. Let us move to third problem. How structure factor is defined. Structure factor is of k. So as you know, this is just Fourier transform of, let me write, Fourier transform of G of R. So it is defined like S of k is like, apart from some prefactor, we can adjust that prefactor, e to the power I k r G of R dr integrated over minus infinity to plus infinity. So this will be S of k, the structure factor. Question number 4. Question number 4 is perfect crystal is obtained when. So as I was discussing in the first question, perfect crystal is only possible only you reach absolute zero or minus 273 degrees centigrade, because this molecular level fluctuation will be there as long as you are not uh, at absolute zero degree Kelvin, 0 Kelvin. If you are at some temperature which is greater than 0 Kelvin, then there will be some molecular fluctuation because of the energy kT, kBT. So this energy will be, thermal energy will be always there. So molecule will be getting vibration, thermal vibration due to this kBT energy if T is greater than 0. So if there is molecular vibration, that thing is not perfectly crystal. If you want a perfect crystal where every molecule is completely stagnant, completely fixed, then you have to reach this 0 degree, minus 273 degrees centigrade or 0 Kelvin temperature. If you are at some temperature which is greater than 0 Kelvin, then there will be some thermal energy, and due to that thermal energy there will be thermal energy, and due to that thermal energy there will be molecular vibration. So in that scenario it will not be a perfect crystal. Perfect crystal will be only at 0 Kelvin temperature. Question number 5. Question number 5 is a true false type question. Molecular dynamics simulation is suitable for equilibrium behavior or not. So in molecular dynamics simulation we start with some random configuration, and then we define what are the interaction between the molecules that can be bonded or non-bonded, that can be Lennard-Jones type, that can be spring, whatever potential is there we define that. Then we calculate after each time step, that what is the force acting on each molecule, and from that we calculate velocity, and this way we try to reach the equilibrium. So molecular dynamics simulation is not only applicable to equilibrium, but this also shows us the path to reach the equilibrium. So unlike the Monte Carlo simulation, in molecular dynamics we can also see the trajectory to reach equilibrium. So it is well applicable to the equilibrium scenario, but also it is applicable to see the path in the molecular dynamics simulation. We can see the path following which trajectory it can reach the equilibrium. So it is applicable. In equilibrium. Okay. So next question: a polymer is called hydrophobic. The question is something. So is called what? So that hydrophobic is the answer. If it is insoluble. So now if something is soluble in water, so suppose water molecules are there and you put something inside water, some polymer chain or something like that, and if it is forming hydrogen bonding with the water molecules, then it is soluble, easily soluble inside the molecule, and in that case it will be called we call it as hydrophilic. So philic means it is loving the association with the water. But in case suppose this hydrogen bonding is not possible, so these hydrogen bondings are not possible in that case, so if we put some chain inside water, that will displace some of the water molecules, and there are already existing hydrogen bonding between the water molecules. So this kind of hydrogen bonding is present already between the water molecules, and due to presence of this long polymer chain, now some of this hydrogen bonding will not be there. So the hydrogen bonding between the water molecules will be disturbed, and water will not like that scenario. So in that case, it will try to push the polymer chain into a configuration which is very collapsed if it is not forming any hydrogen bonding with the water. So if it is not forming hydrogen bonding, if it is not soluble inside the water, then we call it hydrophobic. So phobia means it is not favorable to form H bonding. Phobia means it is not liking water, in that sense. Yeah. Okay. So let us move to seventh question. Seventh question is cutoff is used in MC simulation. So suppose let us discuss about Lennard-Jones kind of potential, which is let's say Lennard-Jones 612 kind of potential. So let me draw clearly. 612 Lennard-Jones 612 will be, there will be repulsive part and there will be attractive part, like this, something like this. Correct. So the form of the potential is like V of R is 1 by r to the power 12 minus 1 by r to the power 6. Right. So it is not actually 1 by, it is sigma by. So something like sigma by r, sigma r to the power 6, something like this. So the form will be something like this. And now suppose this potential will go to 0. This potential will go to 0 here only at infinity. R is equal to infinity. So this axis is R, this axis is V of R. So at R is equal to infinity, it will go to 0 ideally. But if we want to calculate the potential interaction between all the molecules up to distance infinity, that will be a huge task. So suppose you have molecules like this. Now you have to calculate pairwise distance between each molecule and what is the interaction strength between that pair, like this. Now if that cutoff distance you want to calculate up to, so what we do actually, we fix the cutoff distance like this and we calculate interaction only if inside this cutoff. So the potential will basically look like this. After this the potential is 0. V of R is 0 here. So this is because improve computational efficiency. So this is very easy to understand that if you are actually calculating potential interaction due to this LJ potential up to very long distance, then you have to calculate the interaction between all possible neighbors up to infinite distance, because this potential will not come to 0 up to infinite distance. So there will be a minimum interaction will be there. So if it is not absolutely infinite. So now for your practical purposes, then you have to fix something like 2.5 sigma or 2 sigma, according to your problem. You can fix your cutoff and you can calculate interaction only if the molecule is inside that radius. So for a particular molecule, you fix the center of a sphere on that molecule and calculate a hypothetical sphere around that of radius this 2.5 sigma or 2 sigma. And if some molecule is inside that radius, then you calculate what is the distance, pair distance between those two molecules, and what is the interaction strength between the, those those pair. If some molecule is outside, something is here or here, we will not calculate any interaction ideally. So we will consider that these two are not at all interacting if it is outside this radius, cutoff radius. So this radius is RC. RC is the cutoff radius. In general, in polymer simulation, we fixed RC as like 2.5 sigma, and this is a good choice and very common choice. But it is not very fixed. You can modulate it at your own choice, like RC is 3 sigma or 2 sigma. These are also possible choices. So 2.5 sigma is a popular choice. Right? Okay. Say 8 problem. Problem number 8 is like van der Waals interaction decays like, as we have already discussed this, it will decay like r to the power 6, 1 by r to the power 6. This is yeah. Question number 9. So why equilibration is needed in MC? Equilibration is needed because, so in MC we start with a random configuration. We don't we start with a completely random configuration, and then we do a set of particular moves, and then we check energy, which is whether the energy is we calculate the energy difference, initial and initial minus final minus initial, and we calculate delta E, which is EF minus EI. And then if delta E is less than 0, we accept that move readily. If delta is greater than 0, we accept that move with the probability exponential minus beta delta E. So this is the scheme of Monte Carlo simulation, and we start with any random configuration and then we perform these kind of moves, and we believe if we perform that sufficiently large number of moves, so you will reach the equilibrium. So initial configuration is certainly not at equilibrium, because we cannot start with the initial configuration which is or which is already at equilibrium. Then there is no point in performing this kind of simulation. So initial configuration is not at equilibrium, and also the thermodynamic properties which we want to calculate, those properties are only defined at equilibrium only. So thermodynamic properties will converge at equilibrium. So this is the both reasons. Suppose you are doing polymer simulation or some simulation with particles inside a box, and you want to calculate what is the uh, pressure inside box or something like that, or so something like Rg of a polymer or something like those properties will only defined if you want to do RG average or something like this. This is only valid in equilibrium. So you have to collect configuration which are already in equilibrium, and then you have to do the average of RG. So for thermodynamic properties, for averaging, you have to reach first equilibrium, and then only you can do the averaging. Yes, something like if you want to do a particle uh, a box full of gas particles, then if you want to calculate what is pressure or something like that, those kind of thermodynamic properties only is defined at equilibrium. We cannot define the pressure, temperature or something like that without equilibrium. These properties are defined, thermodynamic properties, those things are defined at equilibrium. Okay, last question. Question number 10. What are the steps of Monte Carlo simulation? Monte Carlo simulation involves so let's see what are the options here. What are the options? Like velocity calculation, B force calculation, C random number generation, and D energy calculation. Energy calculation. Now, in we are talking about Monte Carlo MC, and in Monte Carlo simulation, so you start with let us discuss the steps once more. Random configuration, you will start with random config. You do a random move, then we calculate what is the delta E. Now if delta E is less than 0, accept. If delta E is greater than 0, accept with probability exponential minus beta delta E. Now when you are going to do this step, accept with probability exponential minus beta delta E, then computationally what you need to do, you have to generate a random number. So some kind of random number generator you have to use, some popular like RAND2 you can use. So RAND2 is greater than less than exponential minus beta delta E, this step. Then accept, and if it is greater than that, reject, something like this step you have to do. So it involves a random number generation. So random number generation is there, and the energy calculation is also there, because you have to calculate first what is the energy of a state after performing some move, and what is the energy, initial energy. Then you have to calculate what is the delta E, which is like EF minus EI. So energy calculation is also there. So these two for MC, but on the other hand, in this case, this will be important in MD, because you have the information about all the interaction between the molecules. So you can calculate what is the force acting on that, and then using the equation that we will discuss later, you have to calculate first force, what is the force acting on the molecules. Then from that you have to calculate velocity, and from that what is the changed position after some time. So these steps are important for molecular dynamics simulation. And for Monte Carlo simulation, energy calculation and random number generation is important. But in the molecular dynamics, there is no random number generation as such. So we have discussed the previous week's assignment. 10 questions were there. We are done. Let us move on to this week. Some sample problem of this week. So yeah, so here we have discussed. So any doubt in this part, you can tell now. So this is week 5 assignment discussion. Now we will discuss some sample problem from week 6. So in week 6 we are mostly discussing about the solution, thermodynamics of the solution. So some question related to thermodynamics can be important here. Suppose one question is that which of these is extensive property? Extensive property. So option is here like pressure, B chemical potential mu, C is temperature, D is entropy. Now we will call something extensive or intensive if depending on if it is dependent on number of particles. So suppose you have one single box, and if you cut that box into two half, if that property is going to change depending on that. Suppose think about volume. If you have a box full of gas and then you are cutting that box into two parts, then if the property is getting halved after cutting the box, then it is a extensive property. So that way the volume is a extensive property, because if you are cutting the box, the volume will be half after that. So volume is a extensive property. But think about temperature or pressure. If you are cutting that box, there will be no change in the individual box after cutting. So pressure and temperature is going to remain same, and in that case pressure and those temperature is like intensive property. Similarly, chemical potential also intensive property. But entropy on the other hand, because entropy is, so if you remember the formula of entropy is kb ln omega. Now this omega is dependent on how many particles you have, because omega is number of microstate, number of microstate. So if you have large number of molecules, you have number of microstate is also large, and then you have large entropy. So in that sense, this omega is dependent on n. So omega is a function of number of particles. So entropy is a extensive property. This entropy is a extensive property. But this is intensive, this is also intensive, and this is also intensive. We have to, because these are not volume dependent. Not volume in the sense, if you are cutting the box half, these are not going to change. Pressure and temperature is not going to change, but the entropy will change, because it is a function of n, total number of particles. So yeah, so next question is like, if you have a free energy function if for phi t given alpha phi a square beta phi to the power 4. Now what is the condition on alpha and beta so that it shows a phase separation always? Now from the lectures we have already seen that if something has to phase separate, then the shape of the free energy function has to be convex. So for convex function, this in this case alpha and beta both needs to be less than 0. Both needs to be less than 0, alpha and beta. So you can try out with some plotting software, or you can try plotting that if alpha and beta is less than 0, then this function is convex. We can try with like if double prime phi will be, so convex means if double prime phi will be less than 0. So from that function f dash phi is 2 alpha phi plus 4 beta phi cube, and if double prime phi is 2 alpha plus 12 beta phi square. Now we can clearly see that phi is always greater than 0, doesn't matter because phi is squared. So if alpha and beta is less than 0, then this quantity is definitely less than 0. If double prime phi is definitely less than 0, and if something is free energy function is convex, then this will definitely phase separate. So the shape should be something like, so f of something like this, f of phi t. So this is free energy, this is volume fraction phi. Suppose this is phi 1, this is phi 2. So if you mix these two, so at in this here, this will be f of phi 1, this is f of phi 2, and this is phi. So you can easily see that the free energy at this point f of phi is higher than what is the mixing property, so it will try to remain as a phase separated solution. It won't try to mix itself. But if it is its shape is opposite to this, something like this shape, then you can calculate what is, suppose this is f of phi 1, this is something f of phi 2, so f of phi will be there and the free energy is lower than this, so it will try to mix. There will be a we can find the phi there. So let me recap once more that you are given f of phi t as some function alpha phi square beta phi to the power 4, and question is what is the condition on alpha and beta so that I can see always a phase separation. Now to see a phase separation, the first condition is that the free energy function should look like a convex function. So to be a convex function, the alpha and beta needs to be less than 0, negative. And we have calculated what is f double prime phi, and we have seen that if alpha and beta is less than 0, that f double prime phi is always guaranteed to be less than 0. So in that case, we will see always a phase separation. Okay. So next question is what is the relation between, so relation between osmotic pressure and chemical potential. So we have calculated already the formula for pi osmotic pressure. So pi of phi is defined as phi f prime phi. It is discussed in lecture in detail, plus f0, and mu s phi is like v of s p plus f of phi minus phi f prime phi. All these formulas are derived in lecture. So now from the let us do this number 1 and this is number 2. So from 1 we can calculate what is phi f prime phi, that is pi of phi plus f of phi minus f of 0. Now in this 2, if we put mu s phi is equal to v of s p f of phi minus pi of phi, we are replacing phi f prime phi from the equation number 1, minus pi of phi minus f of phi plus f of 0. So f of phi will cancel. V of s p minus pi of phi plus v of s f of 0, v of s p minus pi of phi plus mu s 0. We are rewriting Vs into F0 as some other quantity as mu s 0. Mu s of phi is, so this is mu s of phi. So in this way mu and pi is related. So here mu is chemical potential and pi is osmotic pressure. Right, okay. So yeah, so these two formula is derived in lecture. You can check again how these formulas were derived. So using these two formulas, so first we have calculated what is phi f prime phi from the formula number 1. Then we replace that phi f prime phi in the second equation. There will be cancellation of f of phi and we get a simplified formula, and which is the desired relation between chemical potential and osmotic pressure here. Okay, so move to another problem. So concentration of coexisting phase, concentration of coexisting phase can be obtained by So this is in detail discuss that common tangent construction. Let us discuss that idea once more. What is common tangent construction? So if you have some free energy profile, something like it has double minima, something like, oh sorry, uh, something like this. So this is your free energy profile. This side is f of f, this is phi. So if you can draw a common tangent between two minimas like this, then it can be used to derive the concentration of the coexisting phase. So what is the meaning of this? So suppose, so we have already discussed that for phase separation this is absolutely necessary that f double prime is less than 0. We have some point here where f double prime is less than 0 here. So in this point f double prime is greater than 0, here f double prime is greater than 0. In between some point here, these lines, these are the lines for inflection points. Here suppose this is phi star A, this is phi star B. So f of phi star A is f double prime. So these are point of inflection, phi star B. Okay. Now this is suppose phi A, this is phi B. So this point at this regime, this particular middle regime, f double prime is always less than 0. So this regime, that yellow marked regime, this is called unstable, because if you put a little bit of disturbance in this regime, if you are starting with some concentration which is in this regime between phi A star and phi B star, then it is unstable regime. If you are giving a small disturbance to the system, it will immediately phase separate. But now if you are in these two regime where f double prime is greater than 0, this and this blue indigo colored region, sky blue color region, this regime is called metastable regime, because you need a very large disturbance to create a phase separation from this regime. So in the unstable regime, small disturbance is needed only to phase separate. In the metastable regime, large disturbance is required. So if you start with some phi which is in between, so some star phi which is in between phi a star to phi b star, then if you are giving small disturbance to the system, it will immediately phase separate because it is in the unstable yellow marked region. But if you are in between, so this is unstable region, this is unstable. But if you are in the region like phi is less than phi a star or phi is greater than phi b star, then you are in the metastable region. So depending on that, you can calculate whether it will phase separate or not. Okay, any doubt? So the phase equilibrium is always characterized by equality of both osmotic pressure and chemical potential. So here we have calculated two property, that pi and mu. So pi and mu at equilibrium. So see, the equilibrium will be characterized by equilibrium is characterized by equality of pi and phi both. So this is, of course, it is discussed in lecture some point, maybe third lecture probably. Yeah, you can recall where we have derived this formula. We have discussed that equilibrium is characterized by equality of both of these two quantity phi and chemical potential. Okay. So any doubt? So let me recap the problem. That so in this week we are all discussing the solution thermodynamics, whether there will be a phase separation on the between two quantities, whether it will try to mix themselves or it will try to keep them separated. We are trying to see that from a thermodynamics point of view. So for that we need knowledge about some thermodynamic variable like pressure, temperature, entropy, free energy. So free energy is defined as F is minus kT ln Z, whether Z is the partition function. So this kind of thermodynamic variable is important. So in this module that becomes important, and there will be relation between all the thermodynamic variables. So suppose F is E minus Ts, then Gibbs free energy is E plus PV minus Ts. So yeah, so from this you can write like E minus Ts is F, so F is G is F plus Pb. So all these relations are important here, thermodynamic relation between the potentials, different kind of potential, and all these potentials are only defined for some particular configuration. Like F is defined in Vt, H enthalpy is in Pt, something like this. Okay, so those concept is important. Then we discussed what is the condition of uh, free energy function like f of phi, whether it has to be a convex function or convex function, depending on that whether it will phase separate or not. We have done some problem that what is the condition of on alpha and beta to make it possible to phase separate. Yeah, to make it possible that it is phase separating. Then we have found out relation between what is the relation between pi and mu, chemical potential and osmotic pressures. So this is of the solute. You can do the solvent also. There will be phi will be replaced by 1 minus phi, and there will be a similar formula. And the equilibrium is characterized by equality of both of these quantity, pi and osmotic pressure and chemical potential. Then there is this kind of diagram whether we have discussed what is unstable regime, metastable regime. And in the unstable regime, if you give small disturbance, then the system will phase separate. In the metastable regime, on the contrary, you need a very big disturbance to phase separate from this concept. So from this point, you can also see that f of phi, f double prime is less than 0 in this regime, so it will phase separate because there is a convex region here. So yeah, so that regime is unstable. If you are giving small disturbance in the system, it will try to come to some phase separated scenario. Okay. Okay, so that's all for this week. We'll meet next week with some problems regarding next module is molecular dynamics simulation. We'll discuss problems regarding molecular dynamics simulation.